Were we observing a star's final moments unfold before us? That was the question Betelgeuse asked in 2019, and it gripped the world for months. The question light asks is older and stranger. We are watching the universe's entire history through messengers that have never aged, and most of us have never thought about what that actually means. Light, in its most fundamental form, consists of photons, particles of energy that travel at exactly 299,792 kilometers per second through the vacuum of space. These photons are unlike any other particle in the known universe. They possess an extraordinary property that defies our everyday intuition about time and aging. According to physics, photons do not experience the passage of time. From a photon's reference frame, the moment it is created is the same moment it arrives at its destination, no matter how far that journey spans. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Consider the implications of this fact. When you look up at the night sky and see a star, the light entering your eye left that star years, decades, or even millions of years ago. A photon that began its journey from the surface of a distant star has traveled through the cosmic void unchanged. It has not deteriorated. It has not grown weary. It has not accumulated damage or decay from its long voyage. In the photon's own reference frame, no time has passed whatsoever. This is not metaphor or philosophy. It is a direct consequence of Einstein's special relativity, one of the most thoroughly tested theories in all of science. This stands in sharp contrast to everything we observe in the physical world around us. Stars burn out, people age, objects corrode and degrade, energy disperses, entropy increases. The second law of thermodynamics tells us that all ordered systems naturally tend toward disorder, that time has a direction, and that the future will always be messier and more chaotic than the past. Everything we see succumbs to this arrow of time. Everything, that is, except light. The reason photons do not age relates to their lack of mass. Massive particles like electrons, protons, and the atoms that make up our bodies all experience time in proportion to how fast they move relative to an observer. The faster a particle travels, the slower time passes for it. This effect becomes increasingly pronounced as speeds approach that of light. But photons always travel at the speed of light. It is not an option for them, but a requirement of their existence. At the speed of light, time effectively ceases to pass. A photon is truly timeless. This creates a profound asymmetry in the universe. While we age and decay, the photons that carry information across space remain forever frozen in their state of creation. A photon emitted from the sun 8 minutes ago is not 8 minutes old in any meaningful sense. A photon from Andromeda, our nearest large galactic neighbor, released 2.5 million years ago, arrives here unaltered and unchanged. The photons from the most distant galaxies we can observe, which began their journey over 13 billion years ago, carry their original information intact. They are, in a very real sense, windows into the past that have never been dulled by age. This fact reshapes how we understand astronomy and our relationship to the cosmos. When a telescope collects light from a distant object, it is not merely observing that object as it is now. It is gathering and analyzing actual physical particles that were created in that location at an earlier time. The light from a supernova explosion contains photons that were literally created in the moment of that stellar catastrophe. Those photons have crossed the intervening space without changing, carrying with them the exact signature of that explosion, the precise spectrum of elements involved, the exact intensity and wavelength of the radiation released. We have learned to decode these messengers. Spectroscopy allows us to determine the composition of distant stars by analyzing the wavelengths of light they emit. Photometry allows us to measure their brightness and variability. Polarimetry reveals information about the environments through which the light traveled. Every tool of observational astronomy is fundamentally an exercise in reading the messages that ancient photons bring to us. We are not doing anything to these photons. They arrive here in the same state they left their source, and we simply analyze what they tell us. The universe, in this sense, is not a place we observe, but a place from which we receive messages. Those messages take the form of undying photons that refuse to age, that carry no scars from their journey, but arrive as perfect records of the past. Some of these photons have been traveling since the universe was less than 100 million years old. Others were created just moments ago. All of them exist outside of time in their own reference frame, frozen eternally in the moment of their creation, yet somehow continuously arriving at destinations across the expanding cosmos. This is what makes the study of distant objects so remarkable. We are not guessing about the universe's history. We are not constructing theories in the absence of data. We are receiving actual physical evidence, traveling through space in the form of particles that have never aged, that carry information from epochs we can never visit in person, that represent the universe speaking to us directly across billions of years of cosmic history. To understand why a photon cannot age, you first have to understand what aging actually is, not as a biological fact, but as a physical one. Forget wrinkles, forget grey hair, those are symptoms. The actual process underneath is something more fundamental, something that operates at the level of particles, entropy, and the structure of time itself. In physics, aging means one thing: you exist inside time, and time moves through you. Before and after are different. The universe you occupy at one moment is not the universe you occupy the next. Something has changed, even if that change is undetectably small. That accumulation of change, the slow, relentless march from one state to a different one, is what aging actually is. It applies to everything that has mass. It applies to everything that can be at rest. It applies to you, to a grain of sand, to a proton floating alone in the void between galaxies. This is worth your close attention. Take a proton, a single hydrogen nucleus, positive charge, sitting in empty space with nothing around it. No radiation, no heat, no other particles, just a proton and the quantum vacuum. Is it aging? By every indication, yes. The current best experimental limits suggest that if protons decay at all, their half-life is somewhere around 10 to the 35th years. Write that out, and it is a number so large it loses all meaning. The age of the universe is roughly 14 billion years, 10 to the 10th, roughly. A proton's decay half-life dwarfs that by 25 orders of magnitude. For all practical purposes, a proton is eternal, and yet in principle, it is not. The proton exists inside time. Quantum fluctuations touch it. The vacuum around it hums with virtual processes. Over spans that make the current age of the universe look like a rounding error, something can happen to a proton. The timeline is absurd, but the category is not. The proton is inside time. Time therefore can do things to it. Electrons are similar. No confirmed decay has ever been observed. The experimental lower bound on electron lifetime stretches to numbers even more enormous than the protons. For any practical definition of the word stable, an electron qualifies. But again, category matters more than timeline. An electron has rest mass. It has a rest frame. It sits inside the fabric of time and participates in the processes that time enables. Decay is not inevitable on any timescale that matters to anyone alive, but it is not categorically impossible. The electron is not exempt from time. It is merely very, very patient. This is the landscape all matter inhabits. Some particles decay in fractions of a second. A muon, which is essentially a heavier version of an electron, lasts about 2 microseconds before transforming into lighter particles. A neutron outside a nucleus survives for roughly 15 minutes. A free pion is gone in tens of nanoseconds. On the other end, protons and electrons push the limits so far that no experiment has ever caught one decaying. But the physics does not distinguish between the muon and the proton in any categorical sense. Both are massive, both have rest frames, both exist inside time, and are therefore, at least in principle, subject to it. The only difference is how much time it takes. Now consider what connects all of these. The muon, the neutron, the proton, the electron. They all have something in common that has nothing to do with their charge, or their mass, or their specific interactions. They all experience proper time. They all have a reference frame in which they are at rest. They all, in the language of relativity, move through time. And because they move through time, Processes can accumulate, quantum amplitudes can build, probability can do its work. Given enough time, even the most stable particle is not guaranteed to be what it currently is. Photons are not on this spectrum. This is the critical point, the one that is easy to state but surprisingly hard to absorb. Photons are not simply at the far end of the stability scale, somewhere beyond the proton with a half-life so large nobody has a number for it. They are not in the game at all. The concept of a half-life does not apply to a photon the way it applies to a muon or a proton. A half-life is a statement about how long a particle exists before it transforms, and that statement requires the particle to be experiencing time. Photons, as will become clear in a moment, do not experience time, not approximately, not in a negligible way, exactly and precisely not at all. The difference is categorical. On one side, you have every particle with mass, slow decaying or fast, long-lived or fleeting, it does not matter. They exist inside time. On the other side, you have particles with zero rest mass, and there is really only one kind that matters here. Photons travel at the speed of light in vacuum, always, without exception. They cannot be slowed down, they cannot be brought to rest, and because of that, they relate to time in a way that is fundamentally unlike anything made of matter. The stability of a proton is a quantitative statement. The agelessness of a photon is a qualitative one. Comparing them is something like comparing how slowly a glacier moves to whether a shadow moves at all. The question is different. Entropy is worth naming here because it sits at the heart of why aging happens. The second law of thermodynamics says that in any closed system, disorder increases over time. Energy spreads out. Structures break down. Information disperses. This is the physical root of aging in any system. The tendency of states to become more disordered, driven by the statistics of enormous numbers of particles. Matter ages because matter participates in this process. Particles interact, exchange energy, accumulate small changes, drift toward equilibrium. A photon, existing outside of time, is not inside any thermodynamic process in the relevant sense. It does not interact with the vacuum over time. It does not accumulate changes. Entropy does not work on it, because entropy requires time to operate, and the photon has none to offer. So the question becomes, why? Why does moving at the speed of light remove you from time entirely? Why does being massless mean you experience zero duration between creation and absorption? The answer is not arbitrary. It follows necessarily from something very specific about the structure of spacetime, and the way that structure was first clearly described. The key is something Einstein worked out in 1905, and it starts with a thought experiment that sounds almost childishly simple. Here is the strange thing about moving fast. It does not just change where you are, it changes when you are. Most people encounter time dilation as a curiosity, a footnote in a physics class, something that happens to astronauts and particle accelerators, but not to anyone living a normal life. That framing undersells it. Time dilation is not a side effect of high-speed travel. It is a fundamental feature of how the universe is structured. And once you see what it is actually doing, the story of why light never ages becomes almost unavoidable. Here is the core intuition, and it is worth holding carefully in your mind. Everything in the universe is always moving through space-time at the same total speed. Not through space alone, through space-time, the combined fabric of all three spatial dimensions and time woven together. That total speed is fixed. It is the same for every object, everywhere, always. What changes is how that speed gets divided up. When you are sitting perfectly still in space, not moving relative to anything around you, all of that fixed budget of motion is being spent on one thing, moving through time. You are burning through your allotment of space-time speed entirely on the time axis. The seconds tick forward and you go nowhere. Now start moving through space. Something has to give. The total is fixed, so if more of your motion goes toward crossing space, less of it can go toward crossing time. Your clock slows down. Not because of vibration or mechanical stress or any physical interference with the clock's workings. The clock slows because time itself is passing more slowly for you. The clock is correct. You are genuinely experiencing less time than someone who stayed still. At everyday speeds, this effect is real, but so tiny it takes atomic clocks to measure it. A plane traveling at cruising altitude accumulates a few hundred nanoseconds of time difference on a transatlantic flight. Real, measurable, confirmed, but not something a human body notices. Push the speed higher though, and the numbers start to become hard to ignore. At 90% of the speed of light, the effect becomes dramatic. Time for the moving traveler slows to roughly 44% of the rate experienced by a stationary observer. Send someone off at that speed and bring them back. What felt like 1 year aboard their ship corresponds to about 2¼ years back on Earth. That is not a rounding error. That is a genuine separation of timelines. Keep pushing. At 99.99% of the speed of light, the factor grows sharply. A traveler moving at that speed ages 1 year while roughly 70 years pass for everyone they left behind. Board a ship at that velocity, spend what feels like a single year in transit, return home, and the world has moved on by 7 decades. The people you knew are old or gone. That is not science fiction. It is the direct, unavoidable consequence of how space-time arithmetic works. The progression continues. At 99.9999999% of the speed of light, the compression becomes almost violent. 1 year outside collapses to about 23 minutes aboard. The gap between the traveler's clock and the outside world becomes so extreme that the traveler could cross enormous distances of space while barely aging at all. Each additional 9 in that decimal forces the ratio higher. The pattern is not subtle, it is relentless in one direction. Faster means less time, more speed means more compression, and the closer you push to the absolute limit, the more radical the effect becomes. This is the long road to zero. What happens at the limit itself? What happens when the speed is not 99.99999% of the speed of light, but exactly the speed of light? No rounding, no approximation, the precise value. The dilation factor does not reach some very large number and stop. It diverges. It goes to infinity. Time slows not by a dramatic factor, but by everything. An infinite time dilation factor applied to any finite duration produces the same result. 0. No time passes. None at all. Not a fraction of a second. Not a Planck time. 0. This is where the photon lives. Not as an approximation. Not as a limit we approach from the outside. Photons travel at exactly the speed of light because they have no choice. They have no rest mass, which means they cannot be brought to rest, which means they always travel at c, which means time dilation is always infinite for them. This is not a special condition that photons happen to be in. It is the only condition available to them. Worth being precise here, because the distinction matters. A particle with mass can travel very close to the speed of light. It can reach 99.9999% and go even further in the decimal. But it can never reach exactly c. There is always a gap, however small, and in that gap time still passes, however slowly. The particle is still aging, however imperceptibly. That gap is the difference between almost nothing and nothing. For a photon, the gap closes completely. There is no almost. The speed is exact, and so the time dilation is exact, and so the proper time is exactly 0. Proper time is the technical term for this. It is the time actually experienced along a given path through space-time, not the time measured by some distant observer, but the time accumulated by the thing itself. For a human sitting still, proper time runs at full speed. For a human on a fast spacecraft, proper time runs slower. For a photon, proper time does not run at all. It is not running slowly. It is not paused. The concept simply evaluates to 0. The photon has a creation event and an absorption event, and between those two events, from the photon side of the accounting, there is nothing, no duration, no gap. Think about what that means for a photon crossing the observable universe. Imagine one of those ancient photons released from the hot plasma of the early universe, 380,000 years after the Big Bang. From Earth, this photon has been traveling for nearly 13.8 billion years. Astronomers can calculate the path it took, the cosmic structures it passed through, the way the expansion of space stretched its wavelength from ultraviolet down to microwave. The journey, described from the outside, is immense. It is one of the longest passages anything in the universe has ever taken. From the photon's proper time, it never happened. The emission and the detection are the same event, not connected by a long journey, collapsed into a single moment with no duration in between. Whatever the photon carried when it was created, it is still carrying at the instant of detection. No time passed during which anything could change. No opportunity for decay, degradation, or any process that requires a before and an after. The photon is exactly as young at arrival as it was at departure, because there was, from its perspective, no time between departure and arrival. This is the clean answer to how light never ages. It is not that photons are built from unusually durable material. It is not that space is gentle to them. It is that aging requires time, and photons have none. The time dilation that becomes dramatic at 90% of light speed, and severe at 99.99%, and extreme at 99.99999%, reaches its absolute endpoint at c, and c is the only speed available to light, whatever the journey looks like from the outside. 13 billion years, 380,000 years, 8 minutes from the sun. From the photon side of the ledger, none of it happened. There is a more precise way to say all of this, and it changes the picture slightly. Time dilation gets you most of the way there. The faster you move, the slower time runs for you, and at the speed of light, the dilation factor hits infinity and proper time drops to zero. That is a clean and satisfying result, but it leaves open a question that is worth pressing on. Why does the geometry of the universe work this way at all? Why does moving faster through space steal time from you? The answer lives one level deeper, in something called a worldline, and once you see it, the whole thing clicks into place in a different way. Every object in the universe traces a path through space-time, not just through space, through space-time. You are doing it right now. You are sitting roughly still in space, but you are moving through time at a full second per second. That path you are drawing through the 4 dimensions of space-time, forward in time, barely moving in space, is your worldline. It is not a metaphor. In relativity, it is a geometric object, as real as a line drawn on paper. Everything that has ever existed has one. Stars have them, planets have them, the coffee cooling on your desk has one, and photons have them too, except theirs are different, in a way that changes everything. Here is the key idea. The proper time an object experiences is not the same as the time on a clock mounted to a wall. It is the time accumulated along that object's specific worldline, measured according to the geometry of space-time itself. For something moving slowly through space, this proper time is almost identical to coordinate time, the kind of time a wall clock measures. They match so closely that for everyday life, the difference is invisible. But for something moving fast, the two numbers start to pull apart. The object accumulates less proper time than the wall clock ticks off. It ages less. It experiences less. Now push that logic all the way to light speed. A photon's worldline is a very specific kind of path. Physicists call it a null worldline or a null geodesic. The word null is doing serious work there. It does not mean empty or unimportant. It means the space-time interval along that path evaluates to exactly zero. Not nearly zero. Not approximately zero for practical purposes. Exactly, precisely, mathematically zero. To understand what that means, think about the space-time interval as a kind of measurement, the relativistic equivalent of distance, but in 4 dimensions instead of 3. When you measure the distance between 2 points in ordinary space, you get a positive number. The distance from one side of a room to the other is real, definite, non-zero. But in space-time, the interval between 2 events combines the spatial separation and the temporal separation in a specific way. And for events connected by a beam of light, those 2 contributions cancel exactly. The spatial part and the temporal part balance to nothing. The interval is 0. This is something worth holding in your mind. 2 events, say, a photon emitted from a galaxy and that same photon arriving at a telescope, are separated by billions of light years of space and billions of years of time. From any ordinary standpoint, those events are enormously far apart, but the space-time interval between them is 0. They are, in the language of the geometry, at zero distance from each other in space-time. Not close. Zero. Every observer in every reference frame will agree on that number. This is the thing about the space-time interval. It is invariant. You can be moving toward that galaxy at half the speed of light, or away from it, or sitting perfectly still relative to it. You will measure different spatial separations and different time separations between those two events. Your clocks and rulers give different answers, but when you combine them into the space-time interval, you always get the same result. For a photon's path, that result is always zero. This is not the universe being generous to photons. This is the universe being consistent with itself. Now here is where the geometry becomes genuinely explanatory rather than just descriptive. Ask yourself what would happen if photons did experience proper time. If a photon had even a tiny non-zero proper time along its world line, that proper time would be an invariant, something all observers agreed on. But it would also be a quantity that changed depending on the photon's speed, which is always exactly c. The only way to get a consistent invariant for a path traced at the speed of light is if that invariant is zero. Any other value creates an immediate contradiction. Different reference frames would have to produce different physics for light, which violates the deepest principle in the whole framework, that the laws of physics are the same everywhere, for everyone, in every state of motion. The geometry is not set up to accommodate aging photons. There is no slot in the mathematics where a photon's proper time could live and remain consistent with everything else. The structure of space-time, specifically the way it combines space and time into intervals, demands that null worldlines carry zero proper time. It is not a special rule written for photons. It is a consequence of the overall geometry, and photons, by being massless and traveling at c, happen to follow exactly those paths. Think about what this means for something like the cosmic microwave background. Those photons were released when the universe was a few 100,000 years old. They have been traveling ever since, through an expanding universe, past galaxy clusters, through the gravitational fields of objects that did not even exist when they started. From our perspective, they have been in transit for nearly 14 billion years. Their worldlines are enormous, stretching across almost the entire observable universe. But the proper time along each of those worldlines is zero. The photon that hits a radio telescope today experienced the same interval of proper time as a photon that was absorbed after traveling 1 millimeter. Nothing. The length of the worldline in spacetime coordinates is vast. The proper time accumulated along it is not. A massive particle cannot do this. A proton or an electron moving fast will accumulate less proper time than a stationary one. That is time dilation, and it is real and measurable. But however fast the proton moves, its worldline is time-like, not null. The interval along it is always positive. There is always some proper time accumulating, always some aging happening, always some non-zero gap between its creation and its destruction. To reach zero, you would need the particle to travel at exactly the speed of light, and massive particles cannot do that. They can approach it asymptotically, burning more and more energy to get closer and closer, but they cannot cross the threshold. Only massless particles, only photons, can follow null worldlines. Only photons get the interval of zero. This is why the result from the previous section is not just a curiosity about extreme time dilation. It is not merely that the dilation factor happens to go to infinity at light speed, producing zero proper time as a mathematical limit. The zero proper time and the null worldline are the same fact seen from two angles. The photon does not age because its path through spacetime has zero geometric length in the relevant sense. That is the geometry enforcing the physics. The math does not suggest it or approximate it, it requires it. There is something almost satisfying about that, and something a little vertiginous. The universe contains a category of path through spacetime along which nothing can be experienced, nothing can change, nothing can happen in the internal sense, and light follows exactly those paths. Not because light is special in some hand-waving way, but because the shape of spacetime makes those paths the only ones available to anything massless. The universe is not doing photons a favor. It is simply built in a way where their aging is geometrically impossible. The whole thing traces back to two rules. and one of them sounds perfectly reasonable, and the other sounds like it should be wrong. The first rule is this: the laws of physics are the same in every inertial reference frame. An inertial frame just means a frame that isn't accelerating. A train at constant speed, a spaceship coasting through empty space, a laboratory sitting still on the ground. The claim is that if you run any experiment in any of those places, the laws governing the outcome are identical. You cannot tell from physics alone whether you are moving or standing still. This is not a controversial idea. It matches intuition. Drop a ball on a train going 200 miles per hour and it falls straight down, the same as it would if the train were parked. Physics doesn't care about your velocity. It only cares about whether you're accelerating. That first rule, for most people, goes down easy. The second rule is the one that causes trouble. The speed of light in a vacuum is exactly the same for every observer, no matter how the source is moving and no matter how the observer is moving. Not approximately the same. Not the same when conditions are right. Always, exactly, 299,792 kilometers per second. Full stop. Here is why that should bother you. Think about two cars on a highway. One is doing 60 miles per hour relative to the road. Another pulls up behind it going 80. From the road, the second car is moving at 80, but from the first car's window, the second car is only gaining at 20 miles per hour. Speeds are relative. They add and subtract depending on who is doing the measuring. This is not just a rule of traffic. It is a deeply intuitive feature of how motion works, confirmed by every piece of moving machinery ever built. Velocities are not fixed quantities. They shift based on the observer. Now put a flashlight on the front of a rocket. The rocket is moving at half the speed of light. The flashlight fires a beam forward. Classical intuition says the beam should travel a c plus the rocket's velocity, 1.5 times the speed of light, at least from the perspective of someone watching from the ground. That is what the car analogy demands. That is what Newtonian physics insists on. It doesn't happen. The beam moves at c, exactly c, from every frame, including the one on the ground watching the rocket go past. The rocket's velocity adds nothing to the light. You could push the rocket to 99% the speed of light and fire that same flashlight, and an observer watching from a stationary position would still measure the beam moving at exactly c. Not c plus the rocket's contribution, just c. This sounds like it should be a contradiction. It sounds like it must be wrong. For a long time, physicists assumed there was an error somewhere, a missing correction, a medium through which light traveled that would explain the discrepancy. Experiments searched for that medium. None of them found it. The result kept coming back the same. Light speed is fixed, universally, stubbornly, without exception. Einstein decided in 1905 to take this seriously, not to explain it away or patch it, to treat it as a fundamental feature of reality and follow the consequences wherever they went. The consequences are severe. If the speed of light is the same for all observers, and if the speed of light equals distance divided by time, then when two observers measure the same beam of light from different reference frames and get the same speed, something else must be giving way. Distance and time cannot both be fixed. The constancy of light speed forces them to bend. Different observers must be measuring different distances and different times, not because their instruments are wrong, but because space and time are genuinely different for them. This is where time dilation comes from. This is where length contraction comes from. These are not separate discoveries or independent assumptions bolted onto the theory. They are the direct, unavoidable arithmetic of taking both postulates seriously at the same time. If physics is the same in all frames and light speed is constant in all frames, then time and space must stretch and compress to make both of those things true simultaneously. There is no other way to make the numbers work. Here is something worth holding in your mind. Before Einstein, physicists treated time as a universal backdrop, an absolute clock ticking at the same rate everywhere, for everyone, regardless of motion. Space was similarly fixed. The universe had a stage, and things moved across it. Einstein's two postulates dissolved the stage. Time became local. Space became local. What you measure as a second depends on how fast you're moving. What you measure as a meter depends on the same. Two observers can measure the same event and come away with different durations and different lengths, and both of them are correct within their own frames. Light's constant speed is what enforces all of this. It is the anchor point. Because c is the same everywhere, everything else has to flex to maintain consistency. The universe cannot allow time to be universal and light speed to be constant at the same time. So time is not universal. That trade was made when the second postulate was written into the structure of spacetime. From there, the Lorentz transformations fall out, the mathematical machinery that tells you exactly how time and space measurements change between reference frames moving at different velocities. They are not approximations, they are exact, and embedded in their structure is the behavior of light at the limit. As velocity approaches c, time dilation grows without bound, approaching a factor of infinity at exactly the speed of light. Proper time at that limit is zero. Not nearly zero, zero. The Null worldlines from the previous section don't emerge from some separate geometric assumption. They are what the two postulates produce when you push the Lorentz transformations to their logical endpoint. This is the architecture of the whole thing. Two rules, written down plainly, and then followed without flinching. The universe did not require separate explanations for time dilation, for length contraction, for the freezing of photons in zero proper time. It only required that light's speed be constant and that physics look the same everywhere. Once those two conditions were in place, the rest had no choice. There is something almost mocking about how compact the foundation is. Centuries of physics, thousands of experiments, a complete revision of how space and time work, all of it sitting on two sentences, one of which most people find obvious, and one of which still feels, if you examine it honestly, like it should be a mistake. It isn't a mistake. It has been tested in particle accelerators, GPS satellites, atomic clocks flown on airplanes, and cosmic ray detectors measuring particles crossing the entire atmosphere. The answer is always the same. The second postulate holds. Everything else, the time dilation, the null worldlines, the frozen photons, is just what you get when you follow the logic wherever it leads. When a photon leaves a dying star on the other side of the observable universe, it carries a record, not a copy, not a compressed version. A complete and exact record of the physical conditions at its source the moment it was born, the temperature, the chemistry, the motion, the magnetic environment. Everything that was true about that star at that instant is encoded in the photon. And because the photon never aged during its crossing, none of that encoding has slipped, none of it has blurred. When the photon finally reaches a telescope after a journey measured in billions of years, what the detector reads is precisely what the star wrote. That is not an approximation, that is the physics. This deserves to settle into your thoughts. The frequency of light is a thermometer. When atoms in a star emit photons, the frequencies they emit depend directly on the temperature of the gas. A hotter source pushes photons toward higher frequencies. A cooler source pulls them toward lower ones. The relationship is precise enough that astronomers can read the surface temperature of a star from its light alone, without being anywhere near it, without sending anything to it. They just catch the photons and measure. And because those photons have not aged during transit, the temperature they encode is the temperature of the source at the moment of emission, not an approximation of it. The original number. The spectrum goes further than temperature. Every element in the universe absorbs and emits light at specific frequencies, a fingerprint unique to each atom. Hydrogen has its lines, calcium has its lines. Iron, oxygen, carbon, magnesium, each one has a pattern nobody else shares. When a photon passes through the outer atmosphere of a star, certain frequencies get absorbed by atoms along the way, and those frequencies go dark in the spectrum. The result is a barcode. Astronomers look at that barcode and read off the chemistry of a star they will never visit. The iron lines tell them how much iron the star has. The hydrogen lines tell them how the star is structured. And again, because the photon carrying that barcode arrived without aging, the barcode is intact. It has not smeared. It has not degraded. It is as clean as the day it was pressed into the light. There is more. The polarization of light carries information about magnetic fields. The Doppler shift of the whole spectrum, whether the lines are pushed slightly toward red or slightly toward blue, tells you whether the source was moving toward you or away from you, and how fast. You can use that to measure the rotation of a distant galaxy, to map the motion of gas clouds, to clock the orbital speed of stars you will never see separately. All of that is extractable from photons that cross the universe without experiencing a second of the journey. This is what it means for a photon to be a perfect messenger. Most information-carrying things degrade. A signal sent through a wire picks up noise over distance. A radio transmission weakens and distorts. Even light through a medium, glass, water, anything with structure, gets scattered and absorbed. But a photon crossing the vacuum of intergalactic space has nothing to interact with, nothing to scatter off, nothing to corrupt the signal. And beyond the physical isolation, the photon is also temporally immune. There is no internal mechanism by which it can change, because change requires time, and the photon has none. Whatever it left with, it arrives with. Did we witness a star's death as it unfolded when we look at a galaxy at redshift 6? In a sense, yes. Those galaxies are being seen as they were when the universe was less than 1 billion years old. The stars inside them, the gas clouds, the first heavy elements forged after the Big Bang, all of it is right there in the photons, preserved. The photons hitting the detector are carrying information that has not been touched since it was encoded during a chapter of cosmic history that is otherwise gone. The stars themselves may have exploded long ago. The galaxies may have merged and transformed into something completely different. But the photons left when those structures were young, and those photons are still young. Then something stranger enters the picture. If you compare those ancient photons to what you would expect from their source, you notice something. The frequencies are all shifted. Everything is redder than it should be. The spectral lines are still there. The barcode is still intact, but the whole pattern has been stretched toward longer wavelengths. This is cosmological redshift, and it is worth being careful about what it is and what it is not. Cosmological redshift is not the photon losing energy the way a battery drains. It is not degradation. It is not the light growing tired from a long journey, which is a phrase people use and which is completely wrong. The photon itself has not changed internally. Its proper time is still zero. The quantum state it was in when it was emitted is, at the fundamental level, the same quantum state it is in when it arrives. What has changed is the space it was traveling through. The universe is expanding. Every year that passes, the distance between galaxies grows slightly larger. When a photon is in transit across that expanding space, the expansion stretches the wavelength of the photon. Not because the photon is doing anything, but because the fabric it is traveling through is getting bigger. The wavelength is a property of the electromagnetic wave, and that wave is embedded in space. As space expands, the wave expands with it. Think of it this way. Draw a wave on a rubber band. Now stretch the rubber band. The wave gets longer. The rubber band did the stretching. The wave just went along for the ride. That is cosmological redshift. The photon is the wave. The universe is the rubber band. The stretching is real and the redshift is real, but the photon is not the agent of that change. It is not decaying. It is not aging. The universe is moving around it. This distinction has consequences. When astronomers observe a galaxy at high redshift and they see that its light has been stretched by a factor of 7, they know something specific. They know the universe was 1/7 its current size when that light was emitted. The redshift is a clock, but it is a clock measuring the expansion of the universe, not the aging of the photon. The two things are completely different processes and should not be confused. The energy of the photon does decrease as the wavelength stretches. Photon energy and frequency are locked together. Lower frequency means lower energy, without exception. So a photon emitted in the ultraviolet and stretched to infrared wavelengths over billions of years arrives with less energy than it left with. Where did the energy go? This is actually one of those questions where the answer is unsatisfying in an honest way. In an expanding universe, energy is not conserved in the global sense. It goes into the expansion itself. This bothers some people. It is worth being bothered by it. But the key point is that this energy change is driven by the geometry of space-time, not by any internal process in the photon. The photon is passive. The universe is doing the work. The record the photon carries survives this. The spectral lines shift together. The barcode stretches. But it does not smear. An astronomer who knows the redshift can correct for it and read back the original spectrum perfectly. The chemistry of a galaxy 10 billion light-years away is recoverable from its photons. The temperature of a star that burned out before the Earth existed is readable from its light. All of this works because the messengers are flawless. They do not add noise. They do not corrupt the signal. They arrive carrying exactly what was entrusted to them, in exactly the condition it was in when the journey began. The reddening of ancient light is not decay. It is the universe stretching, with the photon along for the ride, unchanged. There is a specific moment in the history of the universe when light was set free. For the first 380,000 years after the Big Bang, the universe was a plasma, not a gas, not a liquid, a superheated fog of electrons and protons, so energetically violent that photons couldn't travel more than a short distance before being absorbed and re-emitted over and over again, trapped inside a storm they couldn't escape. Space itself was opaque. Light existed everywhere and could go nowhere. Imagine trying to see across a room filled with thick white smoke, where every photon that leaves your eye gets grabbed and spat back out before it covers a meter. That was the early universe for 380,000 years. Not a dark place, exactly. A blinding, impenetrable place. Light was imprisoned by its own abundance. Then the universe cooled past a threshold. Around 3000 Kelvin, electrons slowed enough to be captured by protons. Neutral hydrogen atoms formed for the first time. The plasma dissolved, and the fog that had trapped photons for hundreds of thousands of years simply cleared. Suddenly, photons had a free path. There was nothing left to stop them. They streamed outward in every direction at once, an eruption of light that crossed the entire observable universe. Astronomers call this moment recombination, and what it released is still out there. It never stopped traveling. This release of light was sudden and catastrophic in its scope. Before recombination, space had been essentially opaque to radiation. The universe was a prison of its own making, held closed by the mutual interactions of matter and energy. When that prison door opened, it opened completely. Within moments, in the cosmic sense of the word, photons that had been trapped and shuffled about in the plasma began their outward journey. They would never return. They would never be recaptured. This escape was final and absolute, a one-way voyage that continues to this day across the expanding void of space itself. Those photons are here right now, not metaphorically, not in some indirect sense. Right now, at this moment, ancient photons from 380,000 years after the Big Bang are passing through the walls of the room around you, striking the ground outside, washing over every radio telescope ever pointed at the sky. They are so numerous and so uniformly distributed that if you could see microwaves, the entire sky would glow with them. Not from any single direction, not from any particular source, but from everywhere at once. The cosmic microwave background isn't a signal from a place, it's a signal from a time, and it fills the entire sky because the source of it surrounded us on all sides. This distinction warrants careful attention. Those photons were not microwaves when they were born. At 3000 Kelvin, the radiation they carried was closer to infrared and visible light, short wavelengths, high energy, nothing like the faint microwave hiss we detect today. What happened to them is what happens to all light that travels through an expanding universe. Space itself stretched. As it stretched, the wavelengths of the photons stretched with it. The same expansion that pushed galaxies apart pulled those ancient photons thinner. By the time they reach us, their wavelengths have been extended by a factor of roughly 1,100. What was once hot infrared radiation now corresponds to a temperature of 2.7 Kelvin, barely above absolute zero. The universe has been stretching these photons for 13.8 billion years, and the stretch shows. But they have not aged. That is the critical distinction, and it is easy to miss if you're not watching for it. The stretching of a photon's wavelength is not a change in the photon. It is a change in the space the photon is traveling through. The photon itself, the actual quantum of light, has experienced zero proper time since the moment it left the early plasma. From its own reference frame, recombination, and your radio telescope are the same instant. There is no journey in between, no duration, no process of wear. The wavelength is different because the universe grew, not because the photon changed. This matters enormously because the information the photon carries is still intact. What the CMB carries is a snapshot, not a blurry one, not a degraded one, a precise, detailed record of the physical state of the universe 380,000 years after its birth. Temperature variations of 1 part in 100,000, ripples in density that would eventually grow into the large-scale structure of galaxies and filaments and voids we see today. The satellites built to map it, COBE in the early 90s, WMAP after that, then Planck, have read that information with extraordinary precision. They've recovered the geometry of the early universe, the ratio of matter to radiation, the seeds of everything that followed. All of that was waiting inside those photons. All of it survived the crossing intact. The signal was never corrupted. The messengers never deteriorated. This is something stranger than it might first appear. Consider what those photons have been through since recombination. They've crossed a universe that has expanded by a factor of 1,100. They've passed through galaxy clusters massive enough to bend their paths through gravitational lensing. They've traveled through vast stretches of near-perfect vacuum and through thin clouds of intergalactic gas. Some of them have been gravitationally blue-shifted as they fell into potential wells, and then red-shifted again as they climbed out. The universe they're traveling through is almost unrecognizable compared to the one they left, and yet they arrive carrying the same quantum information they were born with, the same polarization, the same frequency ratios, the same spectral fingerprint, because nothing about what they traveled through introduced proper time into their existence. They moved through a universe that aged. They did not. The CMB is proof of this in a way that no single photon from a distant galaxy quite manages to be. With one photon, you can argue about sources of noise, about intervening effects, about measurement uncertainty. With the CMB, you have a map of the entire sky built from ancient light, consistent to 1 part in 100,000, matching predictions derived from physics applied to a universe 13.8 billion years old. The coherence of that map is only possible if the photons delivered their information without distortion. Any genuine aging, any internal degradation, any accumulation of quantum noise over the journey would have smeared the signal into something unreadable. The map would be static. Instead, it's a portrait. There's something almost disorienting about pointing a radio antenna at the sky and receiving radiation that last interacted with matter before a single star existed, before any galaxy had formed, before any atom heavier than hydrogen and helium had been forged. The universe we live in now, with its superclusters and spiral arms and rocky planets and everything that lives on them, none of that existed when these photons were released. The universe was smooth, hot, featureless, a nearly uniform plasma just becoming transparent. And the light that escaped from that moment is still here, indistinguishable in its fundamental nature from the moment it was emitted. It passed through 13.8 billion years of cosmic history without being touched by any of it, without aging by a single instant. The photons hitting radio telescopes today are the same photons that escaped the hot plasma of the early universe. Not copies, not remnants, the originals. The standard picture of particle decay goes like this. A particle exists, quantum processes work on it over time, and eventually it transforms into something else. This is not a rare or exotic process. It is one of the most fundamental things the universe does. A neutron outside an atomic nucleus lasts about 15 minutes before it breaks apart into a proton, an electron, and an antineutrino. Radioactive isotopes decay on timescales ranging from fractions of a second to billions of years. Even particles we think of as permanent have, under close inspection, a question mark hanging over them. Protons might decay. The current experimental lower bound on the proton's half-life sits somewhere above 10 to the 34th years. That number is so large it has almost no meaning. It dwarfs the age of the universe by incomprehensible margins. But the point is that the question can even be asked. Protons exist inside time, and that alone makes decay theoretically possible. Electrons might eventually go as well. Whatever the timescale, the logic is the same. These particles are inside the machinery. The machinery runs on time. Given enough of it, almost anything can happen. Photons are not in that category, not because they are unusually stable, not because their decay timescale is very long, but because the concept of decay, as physics defines it, does not apply to them in the same way. Attend to this particularly. Decay is not just a fact about particles, it is a process, it has a structure. Quantum fluctuations must accumulate. Internal energy states must shift. Probability amplitudes must build toward a transition. These are not instantaneous events. They unfold over time, the way a coin spinning on a table eventually falls. The whole machinery of particle decay is powered by the passage of proper time. Without it, none of the gears turn. A particle that experiences zero proper time between its creation and its absorption has no window in which any of this can occur. There is no interval in which fluctuations can accumulate, no gap in which transitions can build. The process that would cause decay simply never gets started. This is the distinction that matters. Most particles are stable in the sense that they last a long time. Photons are different in kind, not in degree. A proton's stability is a statement about how slowly the decay machinery works on it. A photon's immunity to decay is a statement about the machinery not running at all. The difference between those two things is not subtle. One is about a very large number, the other is about zero. Think about what decay actually requires at the quantum level. A particle interacts with the surrounding quantum vacuum. Virtual particles pop into existence and vanish. Energy fluctuates within the limits set by the uncertainty principle. These fluctuations can occasionally tip a particle into a lower energy state, triggering a transition. All of that activity is time-dependent. The uncertainty principle itself relates energy uncertainty to time uncertainty. The two are linked. A process needs time to resolve. For a photon, proper time is exactly zero. There is no time over which the uncertainty principle can let fluctuations accumulate. There is no duration during which the vacuum can work on the photon's internal state. The photon is not interacting with time the way a proton or electron does. It is not even in the same temporal situation. What a photon has is a creation event and an absorption event. That is the entirety of its existence. There is no middle chapter, no duration of being. The photon is emitted, and then at some point, which from its own reference frame is the same point, it is absorbed. Everything between those two events, from our perspective, might be 13 billion years. From the photon's side, there is no between. The gap that decay would need to fill simply does not exist. This is where the language of stability starts to break down. When physicists say a particle is stable, they mean it has a very long lifetime. Long enough that in practice, it doesn't decay. Stability is a statement about time. A photon doesn't have a lifetime in that sense. It has a creation and an absorption and nothing else. You can't say a photon is long-lived any more than you can say a point has a long length. The question is the wrong shape for the object. The CMB is the clearest place to see what this means in practice. Those photons were created roughly 380,000 years after the Big Bang, when the universe finally cooled enough for light to travel freely. They have been crossing space ever since. From our frame, that is nearly 13.8 billion years of flight. No proton could survive 13.8 billion years without at least having the question of decay hanging over it. For these photons, the question never arises. They arrive today carrying the same quantum properties they had at emission. Their frequency has been stretched by the expansion of space. But they haven't decayed, they haven't degraded internally. They are, quantum mechanically, the same objects that escaped the early universe plasma. The universe contains roughly 1 billion of these photons for every single proton or electron. That ratio is staggering. By raw particle count, the universe is overwhelmingly made of photons. Most of them are ancient CMB photons, created near the beginning of time, still here, still intact. They are not here because they survived against the odds. They are not here because they were especially robust. They are here because the process that removes particles from existence, spontaneous decay, had no purchase on them. There was no time in which it could operate. Something almost counterintuitive follows from this. When we talk about the lifetime of a particle, we are implicitly assuming that the particle exists inside time, that it has a before and an after, a duration that can be measured, a window during which something can happen to it. That assumption is so basic, we rarely notice we're making it. It holds for every massive particle ever discovered. It breaks down for photons. A photon doesn't occupy a duration, it connects two events. The only way a photon can cease to exist is if something absorbs it. An atom, a detector, a charged particle. Left alone with nothing to absorb it, a photon in empty space will travel forever. Not because it resists decay, but because decay has no footing. There is an analogy that gets at it imperfectly but usefully. Imagine a fire that can only be extinguished by water. In a desert with no water, the fire burns indefinitely, not because fire is especially durable, because the thing that would end it isn't available. For photons, the thing that would end them is proper time, and proper time isn't available. The extinguishing mechanism is simply absent. The CMB photons will exist until they are absorbed. Some will hit the surface of a planet, some will eventually interact with matter as the universe evolves, but none of them will spontaneously transform into something else. None of them will quietly decay in flight. The universe will change profoundly around them. Stars will die, galaxies will drift apart, the last black holes will eventually evaporate, and through all of it, the ancient light will still be crossing space, unchanged, because the process that changes particles requires the one thing photons will never have. You cannot outlast a process that requires time if you are immune to the passage of time. Here is where the physics starts to feel genuinely strange. Everything covered so far has built toward a clean picture. Photons don't age, they carry zero proper time. Decay has no mechanism by which to touch them. That picture holds. But now push it one step further, and something uncomfortable comes into view. The universe has a direction. Time moves one way. The past is different from the future, and that difference is measurable, predictable, and built into the laws of physics. If photons sit outside time entirely, how do they coexist with a universe that is deeply, structurally inside it? The second law of thermodynamics is the rule that gives the universe its arrow. It says entropy always increases. Disorder grows. Heat flows from hot to cold, never in reverse. A glass falls off a table and shatters. You do not watch shattered glass leap off the floor and reassemble. The equations of motion in classical physics are time-symmetric. They would permit that reconstruction, but entropy forbids it in practice. The future has more disorder than the past. That asymmetry is the arrow, the built-in reason the universe runs in one direction and not the other. Without it, past and future would be physically indistinguishable, and the entire familiar texture of cause and effect would dissolve. This law governs matter completely. A star burns through hydrogen and produces heavier elements. The process is irreversible. That star's entropy is higher after burning than before. The light it emits scatters outward in every direction into an increasingly vast and cold universe. More entropy. Planets form from debris and build structure locally, but only by dumping enormous amounts of entropy outward into space. Life does the same. You are a low entropy pocket in a universe constantly increasing its disorder, and you can only stay that way by continuously expelling entropy into your environment. The second law touches everything, except, apparently, individual photons. A photon does not disorder. It does not accumulate entropy in any internal sense. Nothing inside it rearranges. No states multiply. The second law operates through time. It needs a before and an after, a direction in which disorder can grow. Photons, existing in zero proper time, have no before and after. There is no interior clock against which entropy could accumulate. The photon that left a star 10 billion years ago arrives at a telescope today carrying no more disorder than the moment it was created. The second law simply has no purchase on it. The machinery of thermodynamic decay requires time to run, and the photon provides none. This deserves your attention. The second law is often described as the most universal law in physics. There is a saying among physicists that you can imagine discovering a violation of almost any other law in some exotic corner of the universe. But a violation of the second law would be genuinely incomprehensible. It is that foundational. And yet photons, the most numerous particles in the universe, outnumbering protons and electrons by roughly 1 billion to 1, are immune to it at the individual level, not because they are special exceptions the law forgot to include, but because the law's mechanism requires time and photons have none to offer. Then something more complicated comes into view. Look at photons not one at a time, but as an ensemble. The cosmic microwave background contains the largest collection of photons we can observe. These are ancient. They were produced roughly 380,000 years after the Big Bang, carrying the energy signature of a universe at about 3000 Kelvin. In the time since, those photons have been stretched. The expansion of space has pulled their wavelengths longer and longer, from ultraviolet down through visible, through infrared, through microwave. They now correspond to a temperature of about 2.7 Kelvin. Their energy has dropped by a factor of more than 1,000. Where did that energy go? This is not a simple question. In an expanding universe, energy is not conserved in the straightforward way it is locally. The energy the photons lost went into the geometry of space-time itself, into the fabric of the expanding universe. This is thermodynamically real. The universe's evolution is partly shaped by this energy transfer. The cooling of the CMB is part of the thermodynamic story of the cosmos. So while each individual photon is frozen in its own proper time, the collective behavior of photons across the universe is participating in the thermodynamic evolution of everything. The ensemble follows the arrow of time even while its individual members are immune to it. This is one of the stranger features of the physics, and it does not resolve neatly. The same object, a photon, is simultaneously frozen from its own reference frame and actively evolving when considered as part of the universe's reference frame. There is no contradiction in the mathematics. The Lorentz geometry handles it cleanly, but it means that the question of whether a photon is subject to the arrow of time has two correct and opposite answers depending on the scale at which you ask it. Ask about one photon's internal clock and the answer is, there is no clock, there is no arrow. Ask about what 1 billion photons do to the geometry of an expanding universe over billions of years, and the answer is, they participate fully in the universe's thermodynamic story. This dual nature has no clean everyday analogy. Nothing in ordinary experience works like this. An ice cube melts and participates in entropy. A clock ticks and ages. The objects around us are either inside time or outside it, and everything we encounter is firmly inside it. Photons straddle the boundary in a way that has no parallel, and the physics of the boundary is still one of the genuinely open questions in cosmology. How exactly energy is transferred from photons to the geometry of an expanding space-time, and how that interacts with thermodynamic accounting, remains an area of active work. What is clear is this: the arrow of time comes from entropy increasing. Entropy increases because time moves forward, providing the dimension across which disorder can grow. Photons have no such dimension available to them individually, but the universe that photons travel through does have it, and the geometry of that universe acts on photons regardless of their frozen internal state. The photon experiences nothing. The universe experiences the photon's existence and responds to it thermodynamically, stretching its wavelength, absorbing its energy into the structure of space-time, incorporating it into an evolving story that the photon itself cannot witness. Individual photons do not experience time, but the universe they travel through does, and the difference between those two facts is where most of the interesting physics lives. Gravity bends light, and this is not a metaphor or an approximation. In 1919, a British expedition sailed to the island of Principe, off the west coast of Africa, to watch a total solar eclipse. The plan was specific. During totality, when the moon blocked the sun's glare, stars near the edge of the solar disk would become visible. If Einstein was right about general relativity, those stars would appear slightly shifted from their true positions, nudged outward, because the sun's gravity was bending their light as it passed. Arthur Eddington measured the positions. The deflection was exactly what Einstein had predicted. This was the experiment that made Einstein famous overnight. It was also the moment the world learned that gravity does not just pull on matter, it pulls on light too. The reason goes deeper than a simple force acting on a photon. Gravity, in Einstein's picture, is not a force at all in the classical sense. It is a curvature of spacetime. Massive objects warp the geometry of the space and time around them, and everything moving through that region, matter, radiation, anything, follows the curves. Photons are no exception. They travel along the straightest possible paths through spacetime, and when spacetime itself is bent, those straight paths curve. A photon passing near the sun is not being deflected by a force. It is following the geometry of a warped spacetime, doing exactly what a freely moving object is supposed to do. Keep this in focus. The bending of light by gravity is not a small correction or a minor perturbation. Near massive enough objects, it becomes extreme. A galaxy cluster containing hundreds of trillions of solar masses can bend light from objects directly behind it into rings, arcs, and multiple images, a phenomenon called gravitational lensing. Astronomers use this routinely. A distant quasar that would otherwise be too faint to detect becomes visible because a foreground galaxy cluster has focused its light toward us. The universe is full of natural lenses built from gravity, and every photon that passes through them, bent into perfect arcs across hundreds of millions of light years, has not aged a single moment during that detour. Push closer to the extreme, and the picture becomes stranger. A black hole curves space-time so severely that not even light can escape from within a certain boundary. That boundary is the event horizon. But just outside it, at a specific distance, something remarkable happens. Photons can travel in circles. The curvature of spacetime at that radius is sharp enough that a photon moving tangentially stays in a closed orbit, perpetually looping around the black hole. This region is called the photon sphere. The photons circling there have followed their geometry perfectly. They have traveled enormous distances, and every single one of them still carries zero proper time. Nothing about the proximity to the black hole introduces a clock into a photon's existence. The geometry bends the path. It does not start time running. Now consider gravitational redshift. This is a different effect from the cosmological redshift discussed earlier, and it is worth separating them carefully. When a photon climbs out of a deep gravitational well, away from a neutron star, out of a galaxy's core, up from near a black hole's horizon, it loses energy, its frequency drops, it shifts toward the red end of the spectrum. This was predicted by general relativity and confirmed with high precision. One of the cleanest early experiments used a tower at Harvard in 1959. Physicists Pound and Rebka measured the redshift of gamma rays traveling up just 22 meters in Earth's gravitational field. The effect was there, measurable, exactly matching the prediction. Gravity drains energy from climbing photons. When a photon falls into a gravitational well, the opposite happens. It gains energy, its frequency rises, it blue shifts. Both of these effects are real and measurable and significant in certain environments. Near a neutron star, a photon climbing out of the surface loses a substantial fraction of its energy. Near the horizon of a black hole, the redshift becomes extreme. A photon barely escaping can lose almost everything. But here is what none of that is. It is not aging. The photon does not decay. It does not accumulate internal changes. It does not undergo quantum transitions or lose fidelity. Its wavelength shifts because the geometry of spacetime changes from where it was emitted to where it is received. The photon is responding to the shape of the space it moves through, the same way cosmological stretching changes wavelengths as space expands. The mechanism is different, gravitational potential rather than universal expansion, but the principle is the same. External geometry acts on the photon's observable properties. The photon itself remains frozen in zero proper time throughout. This distinction matters because it is easy to look at a photon that has been lensed, redshifted, deflected and conclude that something happened to it. Something did happen around it. The space-time it traveled through was warped, curved, deep, but the photon moved through all of it without a clock. It experienced no before and after. From its side of things, the moment it was emitted and the moment it was detected are not two events separated by time. They are the same event, collapsed into one instant. Whether the path between them was straight or bent into an arc around a galaxy cluster makes no difference to the proper time. Both paths evaluate to the same number, 0. There is something almost clarifying about this. Gravity is the strongest shaping force in the large-scale universe. It builds galaxy clusters, collapses gas into stars, curves the paths of everything. It is the dominant architect of structure at every scale. And yet, for all its power over the geometry of space-time, it cannot do the one thing that would constitute aging a photon. It cannot introduce proper time. It cannot open a gap between creation and detection. It can bend the road beyond recognition. It cannot make the journey take any time at all for the traveler. A photon threading through the gravitational lens of a galaxy cluster, bent into an arc stretching across the sky, arrives at a telescope carrying the same quantum state it had when it left its source. Its frequency may have shifted from the gravitational field it passed through. Its direction may have changed dramatically, but it is not a worn traveler. It is not diminished. It is the same frozen messenger it was at the moment of its creation, indifferent to the gravity that shaped its path. Gravity can redirect a photon, stretch it, squeeze it, but it cannot make it age. There is a version of this that most people run into at some point, and it is genuinely hard to shake. You have just accepted that a photon crosses the universe in 0 proper time. No time passes for it. Its creation and its absorption are, in some meaningful sense, the same instant. And then almost immediately, something in your thinking pulls up short. Because if no time passes, what exactly is the photon doing? Travel requires time. Moving from one place to another place means being here, and then being there, and the word then already smuggles time back in. If there is no time for the photon, how does it get anywhere at all? This is not a naive confusion. It is pointing at something real. The discomfort is correct. Something strange is happening here, and the strangeness does not go away when you look at it more carefully. It just becomes more precise. Here is the picture that helps, though it requires holding two different things in your head at once. There are two kinds of time in relativity, and conflating them is where the confusion starts. The first is coordinate time. This is the time that an observer measures on a clock, sitting at rest somewhere, watching a photon travel from a distant star to a telescope. For that observer, the journey takes billions of years. It is real duration. Clocks tick. The universe expands. Generations live and die. The photon is, from that observer's perspective, genuinely in transit for an enormous span of time. Coordinate time is what you measure from outside the journey. The second kind is proper time. This is the time that accumulates along a specific path through space-time. The time that belongs to the thing making the journey. For a massive object, proper time and coordinate time are related but not equal. Fly fast enough and your proper time runs slow compared to a stationary clock. Come back from a near light speed trip and less time has passed for you than for the person who stayed behind. Proper time is personal. It is the time that the traveler actually experiences. For a photon, proper time is exactly 0. Not small, not approximately 0. Exactly 0 by geometry. The path the photon follows through space-time, what physicists call a null worldline, is a path where the space-time metric evaluates to nothing. No proper time accumulates, regardless of how long the journey looks from outside. The coordinate time is real and can be enormous. The proper time is 0. Both are true simultaneously, and they are not measuring the same thing. This is the piece worth holding carefully. The journey taking 13 billion years is a statement about coordinate time, measured by observers in the universe. The journey, taking no time at all, is a statement about proper time, measured along the photon's own path. These are different quantities. They are not contradicting each other because they are not answering the same question. One describes how long the journey takes from outside. The other describes how much time passes for the thing making the journey. For a photon, that second number is 0. Now, the deeper version of the discomfort. Even granting all of that, even accepting that proper time and coordinate time are different, there is still something that feels wrong about saying the photon has no experience of traveling. If source and destination are the same event for the photon, What does it mean for the photon to be at different places? Position is a spatial concept. It should not require time. But motion does. And if the photon has no time, it seems like it cannot move, which means it cannot go anywhere, which means the journey cannot happen. The logic feels airtight, and also clearly wrong, because photons do cross the universe. The resolution comes from the space-time interval. In relativity, the separation between two events is not measured by space alone or time alone. It is measured by a combination, a single quantity called the space-time interval, which mixes spatial distance and time separation in a specific way. For most pairs of events, this interval is a real number, either positive or negative depending on whether the events are separated more by space or more by time. For events connected by a light-speed path, the interval is exactly 0. This is not saying the events are at the same place. The star where the photon was emitted and the telescope where it was absorbed could be on opposite ends of the observable universe. Spatially, they are enormously far apart, but the space-time interval between them, the combined measure of their separation in the full four-dimensional geometry, is 0. Zero interval means something precise. It means those two events are connected by a path that light can travel. It does not mean they are the same location. It means the geometry of spacetime evaluates the separation between them when space and time are combined in the right way as nothing. The photon's journey connects two events whose spacetime distance is exactly 0, even though their spatial distance is vast. This is why there is no contradiction. The photon is at one place and then it is at another place, and the spacetime geometry between those places, measured correctly, evaluates to nothing. The travel is real. The zero proper time is real. They are both describing the same geometry from different angles. Think of it this way. On a flat map, 2 points can be far apart in horizontal distance and far apart in vertical distance, but still be connected by a path of a specific measured length. The spacetime interval is a similar kind of measurement, just with a geometry that allows it to reach 0 for light-speed paths. The spatial distance is enormous. The time separation, as measured by observers, is enormous, but the combined space-time separation, the interval, is nothing. That is not a paradox. It is just how the geometry works when you stop treating space and time as independent. What makes this hard is that our intuition was built for a world where space and time do not mix. In everyday life, the spatial distance between two places and the time it takes to get there are completely separate numbers. You can walk faster or slower and change the time without changing the distance. Space and time feel like different currencies that do not convert. Relativity says they do convert, and at the speed of light, they convert in exactly the right ratio to make the interval 0. Light moves through space and time simultaneously in exactly the proportion that cancels them out. There is something almost mocking about how clean this is. The universe did not just make photons fast, it made them fast in precisely the way that causes the two pieces of space-time separation, space and time, to cancel each other exactly. The result is a particle that travels across billions of light years without experiencing any of it, from a destination that is, by the universe's own accounting, 0 distance away in space-time. The spatial distance is real, the coordinate time is real, the proper time is 0, and the space-time interval is 0. Every one of those statements is correct. The journey takes 13 billion years from the outside and no time at all from the inside, and both of those are true at the same time. Every photon is carrying a message, not a rough impression of a message, not a summary or an approximation, a complete, exact record of the conditions at the moment and location where the photon was created. The temperature of the source is encoded in the frequency. The chemical composition is written into the spectrum. Specific elements absorb and emit at specific wavelengths. Like a fingerprint, no two sources share exactly. The velocity of the source relative to Earth is preserved in the Doppler shift. The presence of magnetic fields leaves its mark on the polarization. All of it, packed into a single particle, crossing the universe for billions of years, arriving intact. This is not how most information storage works. Think about what happens to a message left in any physical medium over time. Paper yellows and breaks down. Ink fades. A hard drive accumulates read errors at the bit level. The longer it sits, the more the signal drifts from what was originally written. Magnetic tape degrades. even DNA, which evolution has spent billions of years optimizing as an information carrier, mutates. Every biological system that stores information has repair mechanisms running constantly, because without them the data corrupts. The second law of thermodynamics is patient. Given enough time, it wins. In each case, the underlying problem is the same. Information degrades because the system storing it is subject to time's effects. Chemical bonds break. Electrical charges leak away. Mechanical defects accumulate. The fundamental issue is that any physical object embedded in time becomes subject to the thermodynamic processes that time enables. Entropy increases. Order decreases. What was pristine becomes damaged. The universe, by its deepest laws, drives information toward disorder. A photon crossing the universe for 13 billion years has none of those problems. None. The frequency is exactly what it was when the photon left its source, before accounting for cosmological redshift, which is a stretching of the photon's wavelength by the expansion of space. A geometric effect, not degradation. Strip out the redshift, and the information underneath is pristine. The spectral lines are where they should be. The polarization is what it was. The photon has not drifted, not picked up noise, not lost fidelity in any meaningful sense. It delivers its record with the same precision it had at the moment of creation. Consider this fundamental principle carefully. This is only possible because the photon never aged. That connection isn't incidental, it's the whole explanation. Aging, in the physics sense, means experiencing the passage of time, and experiencing time means being subject to all the processes that time enables. Quantum fluctuations, internal transitions, coupling to the vacuum, spontaneous changes in state. Every one of those processes is a mechanism by which information can be lost or corrupted. A particle that ages is a particle that can change. A particle that changes is a particle whose original message can be altered in transit. The photon is immune to all of this, not because it is particularly robust or well shielded, but because those processes require proper time to operate. And the photon's proper time is exactly zero. There is no gap in which anything can happen. This makes the photon categorically different from every other information carrier we know of. Not better by a large margin. Not extremely durable. Categorically different. The distinction is between something that lasts a very long time and something for which time does not pass. A message written on titanium might survive millions of years. A photon survives indefinitely without degradation because there is no temporal machinery working against it. This invulnerability to time's damage gives photons a role in science that no other particle can fill, a role as the universal witness to cosmic history. The practical consequences of this are enormous, and most of them go under the label of astronomy. When a spectrograph on a modern telescope splits incoming light into its component wavelengths, it is reading a record that was encoded billions of years ago under conditions that no longer exist anywhere in the observable universe. The stars that produce those photons are gone. The galaxies they belong to have merged, transformed, evolved past recognition, but the light those stars emitted still carries their exact chemical signature. Astronomers can identify hydrogen, helium, carbon, iron, oxygen, elements present in a stellar atmosphere more than 10 billion years ago, because the photons encoding that information arrived without a single bit corrupted. This is why the spectrum is one of the most powerful tools in all of science. The 19th century physicist Gustav Kirchhoff realized that each element produces a unique pattern of spectral lines, bright or dark depending on whether light is being emitted or absorbed. That pattern is a fingerprint. And because photons carry that fingerprint across any distance without alteration, a spectrograph can read the chemistry of objects so far away that their light left before the Earth existed. The universe's entire chemical history is written in the light, and the light has been preserving that history faithfully for as long as it has been in flight. The power of this capability becomes apparent when we consider what it enables. Telescopes are not merely looking at the universe as it appears now. They are reading the archive of the universe's past, written in photons that have been traveling through the cosmos as faithful messengers. Because those messengers preserve information perfectly, distant observations yield direct evidence about conditions billions of years in the past. We can test theories about stellar evolution, galaxy formation, and the early universe not through simulation or inference, but through direct examination of light that actually left those distant events. There is something almost strange about the scale of this. A star explodes 12 billion light-years away. In the final moments before collapse, the star's outer layers are rich with specific elements, moving at specific velocities, glowing at specific temperatures. Photons leave that explosion carrying a precise record of those conditions. For 12 billion years, those photons travel through expanding space, threading past galaxy clusters, bending slightly around concentrations of mass, losing energy to the expansion of the universe. Then they arrive at a telescope, and a detector reads them. And the record is still there, complete. The explosion's chemistry, velocity, temperature, recoverable after 12 billion years of transit, because the messengers never changed. Compare this to anything else. A rock carried across a continent accumulates scratches, erosion, contamination. A signal transmitted through any physical medium picks up noise at every relay point. Even light traveling through a medium, glass, water, air, scatters and absorbs. But light in vacuum has no medium to interact with, and its own internal structure does not evolve because it has no internal clock. It is, in this specific and technical sense, a perfect carrier. This is also why the cosmic microwave background is so scientifically valuable. Those ancient photons, released 380,000 years after the Big Bang, carry temperature fluctuations imprinted on them at the moment of release. Tiny variations across the sky that encode the distribution of matter in the early universe. The fluctuations are small, roughly 1 part in 100,000. They have not been smoothed out, averaged away, or corrupted by the journey. They are as sharp today as when they formed. Researchers can read the density variations of the early universe directly from this ancient light, because the photons preserved that information without loss across 13.8 billion years of travel. That precision is the foundation on which modern cosmology rests. Every time a telescope resolves a distant quasar, every time astronomers map the chemical composition of a galaxy cluster, every time a gravitational lensing survey recovers the structure of dark matter from the distorted shapes of background galaxies, all of it depends on the same underlying fact. The photons arrived carrying exactly what they left with. Not approximately, exactly. The only reason any of that works, the only reason a telescope pointed at the early universe actually tells you about the early universe, is that the messengers never aged during the crossing. Here is a question the physics actually raises and doesn't cleanly answer. Everything covered so far has described what happens to a photon from the outside, from the perspective of an observer watching light cross the universe. Zero proper time accumulates. The space-time interval evaluates to zero. The photon arrives unchanged. All of that is solid physics, confirmed by experiment, consistent across every reference frame anyone has ever occupied. But there is a different question hiding underneath it, and it is one the equations handle with something that looks almost like evasion. If zero time passes for a photon, if its creation and its absorption are in some meaningful sense the same event, does the photon experience any of it? Does it have a perspective at all? They describe time dilation for a traveler, moving at 90% the speed of light, then 99%, then 99.9. The pattern is clear. As the speed climbs, proper time slows. Push the thought experiment further, and the number keeps shrinking. At 99.9999% the speed of light, a year outside compresses to minutes aboard. The natural instinct is to keep pushing, to imagine the limit, to ask what happens when you reach exactly light speed. The answer that drops out of the mathematics is zero. No time. Instantaneous. And it is tempting to take that number literally, to imagine a photon blinking into existence and immediately blinking out, its entire journey happening in the same frozen instant. This is where the physics starts to resist. The zero is real, but the framework that produces it quietly breaks down at exactly that moment. Here is the specific problem. In special relativity, when you want to describe the world from the perspective of a moving observer, you use a Lorentz transformation, a set of equations that converts measurements from one inertial reference frame to another. These transformations are what produce time dilation in the first place. They are precise, they are consistent, and they work for any observer moving at any velocity below the speed of light. The key phrase is below. When you try to apply a Lorentz transformation to an observer moving at exactly the speed of light, the equations become singular. The transformation factor, the number you use to convert measurements between frames, goes to infinity and the math collapses. The reference frame cannot be constructed. It does not converge to an extreme case. It ceases to exist as a mathematical object. What this means is that there is no valid inertial reference frame for a photon. Not one that is hard to build. Not one that requires unusual tools. One that the mathematical structure of special relativity simply does not permit. The question, what does the universe look like from a photon's perspective, does not have an answer the way, what does the universe look like from a spaceship doing half the speed of light, has an answer. The photon's perspective is not a perspective the theory recognizes as coherent. This is worth holding carefully in your mind, because it changes what it means to say zero time passes for a photon. When physicists say a photon experiences zero proper time, they are making a statement about a limit, about what happens as you take particles with very small mass, moving at speeds very close to light, and extrapolate toward the boundary. The extrapolation is consistent. The physical interpretation is meaningful. There is nothing sloppy or speculative about it. But it is not the same thing as saying a photon has a reference frame from which it observes its own journey as instantaneous. The photon does not observe anything. The machinery of observation, measuring rods, clocks, the whole apparatus of a reference frame requires a massive observer, something with non-zero rest mass that can actually be brought to rest in some frame. A photon cannot be brought to rest, ever, in any frame, by any method. The concept does not apply. So we arrive at something genuinely strange. The proper time along a photon's world line is zero. Every observer in every reference frame agrees on this. It is an invariant fact about the geometry of spacetime. But asking what the photon experiences as it traverses that world line is a category error, not because the question is too hard to answer, but because the concept of experience requires exactly the kind of temporal structure the photon does not have. Think about what experience actually requires. It requires a before and an after. It requires that some moment came earlier and some moment came later, that there was a sequence of states, that something changed. For a massive observer moving near light speed, these things still exist. They are compressed, attenuated, but there is still an ordering. The traveler who ages 5 years while the outside world ages 500 has a sequence of moments. They remember boarding the ship. They do not yet know what they will find when they land. That temporal ordering, however stretched, is still real for them. For a photon, there is no such ordering. Emission and absorption are not two events separated by a compressed interval. From the only description the mathematics permits, the external one, they are two events connected by a null path, a path of zero spacetime length. There is nothing between them, not a compressed something, nothing. This does not break any of the physics discussed earlier. The photon still crosses the universe intact. The information it carries still arrives undegraded. The CMB photons are still ancient and still pristine. All of that stands. What changes is the language. Describing this as the photon experiencing its journey instantaneously is a useful intuition pump, a way of making the zero feel vivid and concrete. But it is technically an overreach. There is no experience. There is no journey from the inside. There is an emission event, an absorption event, and a geometric relationship between them that the theory of relativity describes with extraordinary precision. Physicists are careful about this distinction, even if popular explanations rarely are. Richard Feynman used to push students hard on exactly this kind of question, not to undermine the physics, but to prevent the comfortable misunderstanding from calcifying into something harder to dislodge later. The photon is not a tiny traveler frozen in time. It is a quantum of the electromagnetic field, and the framework that governs it does not assign it an internal clock or an internal experience. It assigns it a world line. And along that world line, the proper time integral evaluates to zero. Some people find this more unsettling than the original claim. The idea of a photon experiencing its journey as instantaneous is strange, but it is at least a picture you can hold, the more accurate version, that there is no perspective to occupy, no experience to have, no inside to the journey at all. is harder to visualize because there is genuinely nothing to visualize. The mathematics describes it precisely. The imagination has nowhere to go. The proper time is zero. That part is solid. But what, if anything, that means for the photon itself is a question the equations decline to settle. The universe contains roughly 1 billion photons for every single proton and electron. Hold that number for a moment, because it is easy to read past it. 1 billion to 1. For every atom of hydrogen, every proton in a stellar core, every electron orbiting a nucleus anywhere in the observable universe, there are approximately 1 billion photons. Most of them are not starlight. Most of them are not the light streaming from galaxies or the faint glow of distant quasars. Most of them are CMB photons, the ancient radiation left over from the early universe, still filling every cubic centimeter of space, still traveling in every direction, still carrying the imprint of a time before any star had ever formed. This is worth sitting with. The universe as we usually picture it is a place of matter, of galaxies and gas clouds, and planets, and chemistry, and on at least one small rock, biology. That picture is not wrong, but it is dramatically incomplete. By sheer number, the universe is not a place of matter at all. It is a place of light, ancient, frozen, ageless light, with matter distributed through it like a thin mist. If you wanted to represent the universe accurately by count, you would draw 1 billion points of light for every single point of matter. The matter, the stuff that forms stars and planets and everything that has ever lived, is the rare exception in a cosmos that is overwhelmingly photons. Here is something stranger still. Those CMB photons were created roughly 380,000 years after the Big Bang, at a moment when the universe had cooled enough for electrons and protons to bind into neutral hydrogen. Before that moment, photons were constantly absorbed and re-emitted by the hot plasma. They could not travel freely. Then the plasma cleared, and they streamed outward, and they have been traveling ever since. Zero proper time has passed for them. While the universe around them evolved across 13.8 billion years, those photons have not experienced a single moment of it. They were present at the beginning of the transparent universe. They are present now. From their side of the ledger, those two moments are the same event. Think about what that means for everything that happened in between. Galaxies assembled from clouds of hydrogen and dark matter. Stars ignited, burned, exploded, seeded space with heavier elements. Second-generation stars formed with rocky planets. On at least one of those planets, molecules arranged themselves into self-replicating structures, and eventually, across billions of years, into creatures that could build radio telescopes. All of that, the entire history of structure in the universe, unfolded in the gaps between photons that were never touched by any of it. The CMB photons were there for all of it and experienced none of it. They are, in the most literal physical sense, unchanged since before the first star turned on. There is something almost unsettling about this when you look at it directly. The universe's most numerous constituent has been absent from its own history. These photons did not participate in the formation of galaxies. They did not get caught in stellar interiors and reprocessed. They did not become part of any chemical reaction or biological process. They ghosted through everything, carrying an ancient record, touching nothing. They are present in every corner of the observable universe, including the room where you are sitting right now. Roughly 400 CMB photons pass through every cubic centimeter of space on Earth every second. Ancient, frozen, untouched by the last 13.8 billion years of cosmic history. This reshapes what the universe actually is in a quiet but significant way. The standard story treats time as the medium through which the universe evolves. Matter changes, stars are born and die, entropy increases, complexity arises and eventually disperses. That story is true for matter. But for photons, especially these ancient photons, there is no evolution. There is no before and after. There is only the frozen moment of creation and the eventual moment of absorption, with nothing between them that the photon experiences. The universe is not simply a place where things happen over time. It is a place where one kind of thing, matter, happens over time, while another kind of thing, light, exists outside of time entirely. Both are present everywhere. They occupy the same space. But they are subject to completely different rules. The ratio of photons to matter carries another implication worth holding in your mind. It means that if you are trying to understand the universe's contents, ignoring the photon background is like trying to understand the ocean by studying only the fish. The CMB is not background noise in the cosmic story. It is the dominant constituent by number. It is the context inside which all of matter's history has played out. Every star that has ever formed, every galaxy that has ever assembled, every planet that has ever developed, all of it happened inside a photon bath that outnumbered the matter by 1,000,000,000 to 1 and was entirely indifferent to what the matter was doing. There is also something to be said about what those photons represent in terms of memory. Matter forgets. A proton today carries no record of where it was 1,000,000,000 years ago. It has been through stellar cores, supernova shockwaves, interstellar clouds. The information about its history has been scrambled beyond recovery. Photons are different. A CMB photon arriving at a telescope today carries, perfectly intact, the spectral fingerprint of the plasma it last interacted with 13.8 billion years ago. Its polarization encodes the distribution of matter at the moment of decoupling. Its tiny temperature fluctuations map the density variations in the early universe that eventually seeded every galaxy that exists. The photons never lost that information because they were never subject to the processes that would corrupt it. They cannot age, so they cannot forget. What you are left with, when you step back from all of this, is a universe that looks nothing like the one that most people carry in their heads. It is not a vast empty space with matter scattered through it, everything slowly evolving through time. It is a saturated bath of ancient frozen light, present everywhere, ageless, carrying undegraded records of a universe that no longer exists in any other form. Matter swims through this light. Matter evolves, burns, collapses, combines, complexifies, and eventually disperses. The light watches none of it. It was here before the first star. It will be here after the last one, not because it is durable in the way a diamond is durable, but because the passage of time simply does not apply to it. Matter is the exception, the small, time-soaked min, Uriti, surrounded on all sides by ancient light that has never aged a day. Every photon that reaches your eye from the night sky is a message from the past. Not metaphorically, not approximately, literally in the strictest physical sense that relativity allows. The light arriving at your eye right now left its source at a specific moment in history, traveled across space without aging a single instant, and is only just now completing a journey that, from its own reference frame, never took any time at all. Tuck this into your mind. The moon is about 1.5 seconds away in light travel time. When you look up at it on a clear night, you are seeing it as it was roughly 1.5 seconds ago. That gap is almost nothing. It is smaller than the delay between a conductor raising a baton and the sound reaching the back of a concert hall. The sun is 8 minutes away. The light warm in your face on a summer afternoon left the solar surface before you sat down for breakfast. The nearest star beyond our sun, Proxima Centauri, is over 4 years away. The light arriving from it tonight was already traveling when it left, indifferent to everything that has happened on Earth in the years since. Push further out, and the numbers stop feeling manageable. The Andromeda Galaxy hangs in the sky as a faint smear visible to the naked eye from dark sights. The light from it left 2.5 million years ago. When those photons began their journey, our ancestors were making stone tools on the African savanna. Whatever Andromeda looks like right now, we have no access to it. What we have is a perfect undegraded snapshot of a galaxy as it existed before the human species existed. That snapshot arrived intact, every photon in it carrying the same frequency, the same polarization, the same quantum identity it had at the moment of emission. This is only possible because those photons never aged. Think about what would happen if they did. If photons degraded during transit the way matter degrades, they would lose coherence over distance. The signal would smear, frequencies would drift. The spectral fingerprint of a distant star, the precise pattern of absorption lines that tells astronomers what elements are present, what temperature the surface is, how fast the star is moving, would arrive corrupted or unreadable. At some threshold of distance, the photons would degrade beyond usefulness entirely. The universe would have a horizon of visibility set not by the speed of light, but by the survivability of photons. Everything beyond a few thousand light years would go dark. Not because the light couldn't reach us in time, but because it couldn't reach us intact. Cosmology as a field would not exist. The cosmic microwave background, the oldest light in the universe, would have long since disintegrated in transit. We would have no access to the physics of the early universe, no map of the density fluctuations that seeded every galaxy, no way to measure the curvature of spacetime on the largest scales. The universe would be locally legible and cosmically silent. What we actually have is something stranger and more extraordinary. We have a sky that is simultaneously a map of space and an archive of time. Every distance corresponds to a different era. Objects 1 light year away show you 1 year ago. Objects 1 billion light years away show you 1 billion years ago. The sky, if you know how to read it, is not a snapshot of the universe as it currently stands. It is a layered record, a depth of time encoded in depth of space, with every layer perfectly preserved, because the messengers carrying the information never change during the crossing. Were we meant to find this? That is not really a physics question, but it is worth pausing on. The same property of photons that makes them ageless, that zero proper time, that null worldline baked into the geometry of space-time, is precisely the property that makes the universe legible across cosmic distances. The universe is structured in a way that allows the creatures living inside it to look outward and see backward. That access is not limited to nearby stars. It reaches to the edge of the observable universe, 46 billion light-years out in every direction, with every photon from every source arriving with its information undamaged. Telescopes are sometimes described as time machines. This is correct, but the mechanism is often left vague. The reason a telescope is a time machine is not simply that light takes time to travel. It is that light survives the travel without degradation. A telescope pointed at a galaxy 10 billion light-years away is not receiving a faded or garbled version of that galaxy's ancient light. It is receiving the original. The photons entering the instrument today are the same photons that left that galaxy when the universe was young, carrying the same information they have always carried, because nothing has happened to them since they were created. Time passed everywhere except inside those photons. Step outside on a clear night and look up. The light reaching you has crossed distances that took billions of years to traverse and arrived unchanged. The Milky Way overhead is a collection of messages from hundreds, thousands, hundreds of thousands of years back, all arriving simultaneously, all intact. Some of those stars no longer exist. You are seeing them as they were, not as they are, because the photons that left them then have only just arrived. The night sky is not a view of the present. It never has been. The sky is a time machine, and the thing that makes it work has been traveling toward you at 300,000 kilometers per second, unchanged, for longer than you can hold in your head.